Welcome to the course on Objects Modeling. Today's lesson will cover two very different topics, but the goal of both is to obtain a specific transfer function of a system. In the first type of problems, we assume that we are given a nonlinear differential equation describing the operation of the system. It can also be a system of equations. However, transfer functions can only describe linear systems, so we must start by linearizing the given differential equation. We will use the first-degree Taylor series expansion. The formula is presented on the slide. Most of the calculations in the task will involve applying this formula. Linearization will concern the environment of a specific linearization point, the operating point. The task will always include a differential equation, or system of differential equations, a vector of generalized variables, a vector of values of these variables at the operating point, as well as information about which signal is the input signal and which is the output signal. As for the next steps, I have written them here in case anyone would like to use the presentation when learning, but I think it would be best to explain it with a specific example. Suppose we are given a system with a differential equation The vector of generalized variables is the linearization point is Let's assume that the input is the variable x2 and the output is the variable x1. The task is to determine the transfer function of the system by linearizing the system at a given point x0. The first step is to equate the differential equation to 0. It doesn't matter whether we move the terms to the left or to the right. The final result will be the same. Now we need to calculate the value of the function at the linearization point. For each generalized variable, we substitute its value at the linearization point. Now we calculate partial derivatives of the function f of x with respect to subsequent generalized variables. The sign of the partial derivative must be used here. It is that rotated 6. We can't use the letter d here. I encourage you to write subsequent derivatives one below the other. When calculating the partial derivative of any variable, we treat all other variables as constants. Once we have determined the derivatives, we need to calculate their value at the linearization point. You have probably already noticed that a large part of this task is taken up by the formal description. Unfortunately, there is no way to speed this up much. You can't just add a vertical line and a linearization point to the ones on the left, unless the first column was already marked at the linearization point. Please also remember to underline vectors. I treat the lack of underlying as an error. In the next step, we need to write the linearize function. That is, we should use this formula. We therefore see that the calculated derivative at the point should be multiplied by the difference of the variable and its value at the linearization point. There needs to be an approximately sign here, because this is an approximation. We can ignore the terms for the second derivative x1 and for the variable x2 because they are equal to 0. If you want to multiply a bracket by 1, you must include the multiplication sign, otherwise I will assume that you are thinking about a unit step. The function f of x was equal to 0, so its approximation should also be equal to 0. Now one variable on the left side of the equation and the other on the right side. We apply the Laplace transformation on both sides. All tasks will assume 0 initial conditions, so the nth derivative of the signal is transformed into the variable s to the nth power. Only writing the transfer function remains. Remember, this is the ratio of output to input. And this is the result for this task. Given a differential equation, and other information for the task. In order for the system to be able to stay at the linearization point, all derivatives must be zero. So this is usually what it will look like in practice. However, in the tasks, please expect that all generalized variables may be non-zero. This task is about exactly the same thing, that is, we want to determine the transfer function of a linearized system, and the only problem is a slightly more complicated expression. First, define the function, and then calculate its value at the linearization point. The natural logarithm of 1 is 0, so we treat the variable d as a constant, that is, in the component b to the power d, we proceed in the same way as for a variable raised to a specific power. The derivative of the natural logarithm is 1 divided by the argument of that logarithm. And of course times the internal derivative, which is the derivative of b squared. In the case where the exponent is a variable, the derivative is equal to so in our case it will be and once again the internal derivative of d prime squared. I remind you that each vector must be underlined. Now we write the linearized function. Many of the coefficients are 0, so the formula will be rather short. We calculate the Laplace transform of the entire equation. If not all the three terms in the linearized function cancel, we will get a component that is not associated with any of our signals. Let's introduce some new signal here, for example c of s, and let it be equal to 1 over s. Then our equation will take the form and if we leave only the output signal transform on the left side, then this signal c of s can be treated as an artificial input to the object. This artificial input is a constant, equal to 1, so its transform is 1 over s. As a result, we get two transfer functions, for the input b of s and for the artificial input c of s. We can also write this as a transfer function matrix multiplied by the input signal vector. And this is assuming two different input signals, one of which is artificial. But in the task content, we had the information that the input signal should be signal B, so we can ignore the influence of the additional input C on the output signal. Therefore, we are only interested in the transfer function from input signal B. This extra term can be omitted immediately after calculating the Laplace transform of the equation. And one more task of the same type, but this time we will be dealing not with one differential equation, but with a system of differential equations. Since we have two equations, we will also have two different functions. And in fact, we just have to do almost all the calculations twice, until we get the Laplace transforms of the two linearized equations. If a function doesn't depend on any generalized variable at all, there is no need to write its derivative. However, each time one needs to write the subscript of the function that the calculations concern. and the last element can be omitted here. And now the second function and the second equation. And here we have two equations depending on the variable s. According to the task, the input should be signal u and the output signal y, so that w of s is unnecessary. Therefore, from the first equation, I will determine w of s and substitute it into the second equation. Transfer function is the ratio of the output signal to the input signal. And if the task includes information that the results should be on one fraction line and segregated by powers of s, then we already have the first thing, But by segregated, I mean that it cannot be a multiplication of two expressions dependent on S. So I will multiply it in a moment. However, first it would be a good idea to shorten what we can, and if we look closely, this linearized system will actually be of second order, not third. And that was the last task of this part of the class. We will now move on to the second type of systems, that is, electrical systems with passive elements. At the very end, I will present one exception in the form of a specific structure, but more on that later. This task will require the ability to create current equations and voltage equations, Kirchhoff's laws. However, due to the assumption of zero initial conditions in the system, we will be able to simplify some of the calculations. In the standard approach, when we write voltage equations, we must start with equations containing derivatives in the case of inductors and integrals in the case of capacitors. After writing such equation, we should calculate its Laplace transform. And the Laplace transform of the derivative and the integral requires taking into account appropriate initial conditions. But the task content will contain assumption that initial conditions are equal to zero. And at this point I can say that there will be such information in every task you encounter with me. However, if you ever need to solve a task in which the initial conditions are not zero, you can simply use the formulas presented a moment ago. But in our case, we see that we can again simplify this so that the transform of the derivative gives multiplication by variable s, and the transform of the integral gives division by variable s. As a result of this substitution, we obtain the equation of this two-terminal network depending on the complex variable s. Please remember what this equation looks like. However, I would like to propose here an impedance approach to solving this type of tasks. Therefore, each passive element in the diagram can be treated as the same element, only with a different impedance. For a resistor, it is equal to R, for a coil the impedance is equal to SL, and for a capacitor it is 1 over SC. The voltage transform on a given electrical element is equal to the product of the current transform and the impedance of that element. So we get this sum, and as a result, exactly the same equation as before. We can therefore calculate the entire task, from beginning to end, on equations dependent on the complex variable s. This slide is just a reminder of how we calculate the equivalent impedance of series connected components and parallel connected components. This may be useful in some tasks, but it doesn't have to be, and would rather serve to simplify a system scheme. I would also like to remind you about creating current and voltage equations. In terms of Kirchhoff's current law, the sum of currents entering any junction is equal to the sum of currents leaving that junction. In the case of Kirchhoff's voltage law, it is necessary to select any closed loop of the system. The directed sum of the voltages around any closed loop is zero. At this point, I would like to remind you that the direction of voltage should be opposite to the direction of current flow through a given element. 3 example voltage equations are presented on the slide, and the corresponding loops are marked on the circuit diagram. If instead of voltages we write the products of current and impedance, we will get such equations. When it comes to solving tasks, unfortunately I can't yet point to any specific step-by-step method. What helps me is to write at the beginning the transfer function I'm looking for, the quotient of which 2 signals I need. Then, if some part of the system can be simplified, and I don't lose access to the variables I need, then such a simplification is usually helpful. Well, apart from very specific tasks, in the vast majority of cases it will be necessary to achieve a situation in which the expression in numerator and in denominator will depend on only one and the same current. Then it will be possible to shorten it, and all that remains is to segregate the result. Well, at the beginning I mentioned that there will be one exception, and this exception is active quadrupole with an operational amplifier, but exactly in such a connection, where the input signal is the voltage U1 and the output signal is the voltage U2. Then the transfer function of such a system is equal to the quotient of the impedances Z2 and Z1 with a minus sign. However, these 2 impedances can be in the form of several interconnected elements. I will now work through some examples, which I hope will make it easier for you to understand this part of today's classes. Consider the drawn quadrupole. Let's assume that the input signal is voltage U1 and the output signal is current I4. As I mentioned earlier, it's a good idea to start by writing the transfer function so that we can clearly see what we are looking for. We see that we will not need currents 1 and 2. Moreover, we only need current from the last branch. So the entire system can be simplified to the form Neither drawing nor using such simplifications is necessary, but I show it as one of the possibilities. In the case of the first equivalent impedance, we are dealing with a parallel connection, and in the case of the second, with a series connection. Let's look at our transfer function. In the vast majority of cases, it will be necessary to shorten the currents. We have voltage in the denominator, but after substituting the voltage equation, we will have current. So let's start with a voltage equation that preferably contains both the input and output signals. So the loop we are interested in is this. The direction of voltage is opposite to the current direction. One don't have to put it on the scheme, but I will draw it in the first task. So the loop shown earlier will give us such voltage equation. But such notation is rarely useful, so it is better to immediately convert the voltage to the product of current and impedance. If we don't know what to do at the moment, we can substitute what we got into the transfer function equation. We are close. We only need to convert the current I of S to the current I4 of S. For this purpose, we will use the current equation. Now we are disturbed by the current I3 of S. But in the case of currents in parallel branches, it is very simple to determine an equation by which it is possible to convert one current into another. Just write the voltage equation for this little loop. And this is the most enjoyable moment with these tasks, because we are aware that the task has practically been solved. All that remains is to shorten the currents and bring the result to the required form, and in our case also getting rid of the introduced impedance designations. I will immediately reduce this to a common denominator. You have probably already guessed it. The result should be presented on one fraction line and segregated by powers of s. The command segregated by powers of s means to me that s to a given power can only appear once in numerator or denominator, and furthermore, no multiplication of two expressions with the variable s can be left. And this is the final result. The order of terms in numerator and denominator can be any. In the next task, let's assume that we have the same electrical system, but the input signal is now the voltage across the capacitor. And let the output signal be current I1. Although the electrical system is the same, the task is completely different. As usual, let's start by writing the transfer function. We start with a loop that contains both signals. First, I will show you the longer way, and then I will show you how to speed it up. In this notation, I omitted the dependence on the complex variable s. This can be done because I implicitly assume that small variables are time-dependent and large variables are s-dependent. However, one must write upper and lower case letters clearly. It is best if they differ not only in size, but also in shape. However, the written equation will not be of much use to us because it only contains one of the variables we are interested in. Therefore, I will replace the last component with voltage. The voltage U1 is now disturbing us. We must therefore propose some other equation that will contain U1. Let this be a loop containing current I2 and current I4. After substituting U1, we get and to the entire transfer function Now we need to apply such equations that will allow us to convert one current into another. Small loops of parallel branches are best for this. But how to convert the current I4 into I1? Here Kirchhoff's current law will help us. I use the two substitutions I wrote a moment ago. And at this point, I can write the transfer function and apply such substitutions that only the current I1 remains. In denominator, the first and last terms are reduced, which indicates that some calculations were unnecessary. Currents can be shortened. Now we just need to bring the result to the appropriate form. I don't have to multiply that in numerator. One can't leave multiplications of two expressions dependent on s, but the multiplication of a specific value times an expression dependent on s can stay. And this is the correct result for this task. But I mentioned that it could be solved faster. It was unnecessary to use an equation with u1 here. It will be fastest if we only deal with the second small loop. And here this formula is needed. Thanks to this, we immediately move on to the transfer function form . And the rest of the transformations are the same as before. Now let's assume that the input signal is U2 and the output signal is I4. Of course, in this and every other case, we assume zero initial conditions. First, the transfer function. In this case, we can see very clearly that one small loop can solve the task. We substitute and that's the end. So you see that these tasks don't have to be extremely long. This time let's choose typical input and output signals. If so, it means that we can calculate the equivalent impedances in the system. So the simplified circuit will look like this. Two simple loops. And the task is practically solved, only elementary transformations remain to obtain the appropriate form of the result. Mr. Michalski recommends that each term in numerator and denominator be placed in the same order, for example R, L, C. Thanks to this, during multiplication, one can check from the left whether a given letter is repeated. Also, when adding, it is easy to recognize two terms that can be added together. And this is the last task with this electrical system. And this is the example of the task where none of Kirchhoff's laws are needed, just a simple formula for the voltage across the element. Finally, let's move on to the operational amplifier circuit. In this type of tasks, the input will always be the voltage U1 and the output the voltage U2. Therefore, the formula for the transfer function of an object will also always be the same. That is, the first impedance applies only to the coil. And the second impedance is between the capacitor and the resistor. And this is the result. This is the last task, and more of curiosity, it probably won't fit in the 90 minutes of material, so please treat it as an addition. The only difficulty here is determining the equivalent impedances. I will start by redrawing the circuit. And now the subsequent equivalent impedances, starting with the innermost ones. and I will not comment on anything further. I will just bring it to the final result. But since no one will probably want to watch it anyway, I will say goodbye here. Thank you for your attention and have a nice day.